So here I am again looking at bioplastics because that's my project for the moment. And here's something interesting. This um, shreds, and this is a baby wipe. I use them in my laboratory to wash my hands, sort of. If you have a thing about clean hands, playing with shellac is not a good idea. Otherwise, it's perfectly non-toxic. I mean, as long as you make it with non-toxic stuff, right? Okay, so this was the same thing, right? And I just brushed on some shellac, and you can see where I cut it, and it's nice and clean and even. This is the old, like the edge of the thing. And that's what it used to look like. And now it cuts like this, like a piece of plastic. And it's been banging around here. But it's nice and clean. So I can work on it with my high-tech dollar store scissors. Hang on. Okay, one down. And, we cut a small piece off so that it's even all the way around. And I can make that one go away, but I'm not really worried about it. I just wanted it kind of square looking, or, sort of square, rectangularly square. And we can look at it. And I think it's waterproof now. I think I can put a piece of, a few drops of water on there, and it'll just bead up on the surface. But I did not bake this one, and baking it is one of the ways to make it harder and make the bonds between the molecules of lignin that make trees hard and make acetone, make this shellac get harder than most plastics get. Most plastics are about the same hardness as your fingernail, okay? About 2.5 on the Mohs scale of hardness. And wood is a little bit harder than that. Maybe not. Copper is 3 on the Mohs scale of hardness. And that's kind of what I'm aiming at for my biological plastic stuff. This one was just an experiment, and I thought what I'd do is make hinges for my plastic. Let's see. Hold on. Okay, moving right along. Look at that. There's bioplastic number 1 with shellac. You can see it's very, with the acetone. And this is shellac with just alcohol. And I'm not really seeing much difference, except this is maybe shinier. Maybe not. I don't know. This did it in one coat. Okay, I dunked it in. And you can see a nice even line there. And I dunked this one in. But the This one was the second coat. The first coat didn't do very well. So I had to let it set a little bit, and then I dunked it in, and it was fine. And what we have now is a plastic that can be bent, shaped. I can roll it into a flexible plastic. I tried making some hinges, and I don't think that's gonna work, actually. I think we're gonna do separate pieces and make them as hard as steel and put nuts and bolts and things holding them together. But we are playing at the moment and not actually building airplanes. So what we want to do is find out the limits and what it is and what it can do and what it can't do. Because, for instance, what I'd like to do is fill up those interior spaces there with my biological plastic. And what's happened is I have soaked it, so it went in there, and all of those bits and, those little up and down things. Hello, yo, my spiritual advisor, Yoda, singing the song of his people with the washing machine. He does that when he's hunting lizards out in the backyard. Very funny. So, I want to see what happens when it gets baked. And I can add some more layers on, and we'll see what it looks like. Well, I left a portion here in the middle free of both. I just dunked it in one end and dunked it in the other end, and that way we can keep track of what it was like when we first got it. And there you can see sort of some differences in the way that it set up in there. And this is, I think, numero dos. So I do like the acetone plastic better. This is still kind of moist. This is dry. And it's going to be drier by tomorrow. And when you're working with acetone, that's one of the things that the old-timers, like guitar makers, tell you to let it dry overnight. It feels dry, but it's not quite. Or you can put it in the oven. You don't want to put your guitar in the oven, of course, but you can put a piece of cardboard in, and it won't hurt anything. And the interesting thing about this plastic is it doesn't melt like petroleum plastic does. So we've got a method with my silk of turning cardboard boxes into silk purses and stuff. How about that? Making silk purses out of sow's ears, so to speak. And see, it's not just making airplanes, right? I mean, you can make literally anything. Literally anything. You can make plates that are made out of cardboard, but they last a long time because they've got this hard plastic that's non-toxic, right? It doesn't off-gas. This stuff, plastic, this is paper with a plastic coating on it. And any kind of petroleum plastic off-gases. It continues to off-gas through its entire life cycle, which is about as long as the half-life of PT-190 or maybe only plutonium, right? Only 1 billion years, something like that. Maybe it's forever, because the plastic they use from petroleum, they do an operation on it called volcanism, which, you hear that word from me, it means volcanic activity. But in this case, a guy in England back in the 1800s, early 1800s, was trying to get rubber to not disintegrate when they were trying to use it, for balls and bags and rubber bands and stuff like that. And they'd use it a few times and stretch it, and it'd go and break. And so he was playing around with it one day, and he heated it up in the presence of sulfur. Okay, so he was heating it on his stove with sulfur, right? Sulfur, this is it, they didn't know that much chemistry at that point in time, and almost no organic chemistry. And so he was playing like I do. And it happened that it actually worked, and it smelled like the fires of hell because of the burning sulfur. And so he called it volcanism because it reminded him of a volcanic eruption on his stove. And remember, he didn't have a nice electric stove or something. He was cooking on a wood stove, as everybody did in those days. And so it was a discovery that allowed people to start using rubber. And rubber has, let me see, where'd my cardboard go? Here's some cardboard. Rubber and terpenes in general, and little short chain hydrocarbons look like this. Bump, 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 this bumpy stuff here. And there's a carbon, and then hydroxyls. Bump, 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 bump. And the carbon and the carbon will have a hydroxyl attached to it. Carbon, 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 carbon. And we just put the carbons on because it's understood that without the bonds of a carbon ring, carbon requires an oxygen and a hydrogen to just sit there, or two hydrogens. And so they make short chain hydrocarbons that are little sawtooth affairs like that, and they evaporate quickly, or not so quickly, but When, for instance, I've got a whole box of, come on, let's focus. Oh, I used to have a phone that could focus, man. There it is. Come on. No, you can focus now. There you go. Okay. So, I've got a whole box of essential oils, and that's what makes them essential. Their essence smells because they're little evaporative short chain hydrocarbons. And when we burn them, they pretty much burn all the way. They don't leave unburned hydrocarbons like oil does, petroleum oil, because they're not petrified, right? This is just living plant stuff. Paper came from wood, and we don't have to make it from wood. You can make it from cannabis, and you don't have to cut down trees. Think about that, huh? We just about cut the whole fucking forest down in Brazil. I was taking pictures from Google Earth yesterday. And half of that damn rainforest that was there when I was a kid is no longer there. And they're working on the northern half from the north down. And it looks like they're going to join those two. And what they've done is clear cut that whole fucking country. And you know something? Some kid told me he didn't believe in global warming. Well, you know what? I didn't either about 20 years ago. And so I started building computer models that model the various inputs into our weather system. And there's really not as many as you'd think there are, because most of it is controlled by the Pacific Ocean. And that El Nino thing, that's what I started hearing about, that El Nino current. And I thought, man, how can that, something down there, affect northern America and you know, the other continents? Well, it turns out half of our planet is the Pacific Ocean. And if you look on Google Earth, you can see that it literally takes up half of the planet, and the continents are on the other half. And so we go round and round and round, or round and round and round, going everything goes around and around and around, like the continents, okay, and that's what causes the geological things, and the continents in the north turn to counterclockwise. All the plates do. All the tectonic plates turn counterclockwise in the north and clockwise in the south, because as the planet is rolling along, let's see, it's going west to east, okay, west to east, so it's going like this. And what that's doing is creating a force across the top of the planet. And so our North America is turning like this. So is the Pacific. So is Eurasia. And they turn against each other, so does the Atlantic. And below us in the south, they turn the other way, because It's like rolling along. You can see it easier on the just rolling along with the planet. That's what it's doing, just rolling along. And the planet itself is rolling along a magnetic field line from the sun, because the sun is magnetic. Okay, so when that current down in the southern hemisphere heats up, it affects this whole thing up to the equator, right? But when the El Nino thing happens, it's so hot it jumps the equator. It jumps and begins warming this up. And water wants to be the same temperature across the entire surface. And of course, it's too big to do that. But it tries, and it is very even. Under the polar ice on both ends, the water directly under the ice is 3 degrees Celsius, because that's where water is most dense, and the water floats on top. I mean, the ice floats on top of the water because the water is more dense than the ice, and ice is the only thing, water is the only thing that gets less dense when it becomes a solid. And if it were not so, we wouldn't know about it, because there would not be life on planet Earth. It is one of those necessary ingredients for a living planet. When that water right directly under that ice changes, if it gets colder, it gets less dense. From 3 degrees to 2 degrees to 1 degree to 0 degrees, it gets more dense and sinks. Or conversely, if it gets warmer, it also sinks. It has to be that 3 degrees. It's not like optional. And these long, hot summers in the north are not as long and hot as the ones in the south. And thus, that's why that El Nino is so important. And it drives water currents. And it's the water currents we have to worry about warming up. It's not so much the warm air on the continents, it's the warm water under the ice. And when that goes, when that water, that layer of 3 degrees water changes, that equilibrium only has to change a couple of degrees, and that water starts sinking, the ice starts sinking, and it gets below the level of the water, and all of a sudden it sublimates, it changes. Water has this property of being an even temperature all the way across it. Well, underneath the polar ice, that 3 degrees changes to 4 or 5 degrees. Doesn't have to shift like 10 degrees. 2 degrees. 2 degrees is enough. And the entire ice pack will sublimate into water. Change from ice to water in one go. Not a little bit at a time breaking off and all of that like it's doing now. It's doing that just because the atmosphere itself is warmer. And there's more solar energy trapped inside our atmosphere from burning fuels that leave unburned hydrocarbons in the air. Comes from fossil fuels, coal and petroleum oil. Not from burning cannabis oil, not from burning Even wood smoke is, I mean, it smells good, right? It smells good because it is good. It's not bad to burn wood or to burn things that have short chain hydrocarbons. But it is killing us burning fossil fuels. If we don't stop right now, we're not going to be here 10 years from now. Guaranteed.